Okay, starting out with another one of my favorite songs, but I can't play too much of the clip because we got to learn stuff. Anyway, what have we been discussing so far in parts 1 and 2? Well, let's talk about that. We have been discussing brief history of how we came to understand electricity. Electricity at the atomic level, magnetism and electricity, and how they're pretty much always together. Significance of the valence shell. It's a really important concept to know. Flowing things like water and electrons. Coulombs, how'd they get their name? What's the history there? Amperage, same thing. Measuring electricity, how'd we learn to do that? Voltage, we've learned all this stuff. What are we going to talk about now? Well, this time and in the future, probably won't get through all of this, but what are the parts of a simple circuit? We'll get through that. Simplified Ohm's law math. What is an ohm? Intro to circuits. How do we analyze a circuit using Ohm's law? Circuit analysis using Kirchhoff's series laws. What's the difference between a series and a parallel circuit? Circuit analysis using Kirchhoff's parallel laws. And remember, whenever you see red text, you want to record that into your logbook, your engineer's notebook, so you can remember it. Moving on, we need to talk about something called Circle T math. Circle T math, there's a couple of valuable things, reasons why we use Circle T math. What's Circle T math? Well, Circle T math is a circle, and the circle contains the idea. By the way, in the old textbooks, I got a textbook that is over 100 years old, and it actually has this concept in it for electronics. It's a triangle T for the old school people, but it's the same idea. Inside the circle is a horizontal line. This horizontal line or horizontal bar implies divide. It's called the per line, if you've heard it called that before. The divide bar, the divide line is called the per line. Then there's also a vertical bar, and that vertical bar means multiply. Circle T's are used to help us to remember math equations. Write this stuff down. If I go too fast, stop the video and write it down. You remember Georg Ohm? We talked about him in earlier videos. He discovered an important electrical relationship known as Ohm's law. And so to better remember Ohm's law, to better understand Ohm's law, I thought maybe I should talk about it a little bit more. Ohm's law, we're going to use this circle T. This circle T's can be used for any three-part equation, especially if they include multiplication and division, of course. But here's how it works. First of all, we remember Georg Ohm, or George Ohm, was instrumental in finding the relationship between resistance, voltage, or electromotive pressure, and amps, the flow of electrons through wires. So Georg Ohm, he discovered the relationship between volts, and which was named for Alessandro Volta, of course, and amps, which was named for Andre Ampere. And the relationship is named ohms after Georg Ohm, George Ohm, and I was most impressed that he found this relationship as a high school teacher. That's pretty amazing. Anyway, it was named for Georg Ohm. And in this circle T, using the circle T, we can find missing data. For example, assume that we know the electromotive force. That's the same thing as volts, if you don't remember. Electromotive force, if we know what it is, say it's 12 volts, and the current and intensity, we also know that. Let's assume that the current or the intensity is 6 amps. Now, if we know those two pieces of information, the circle T tells us what to do. Because to find the resistance, we can simply divide. We will divide this information. We'll divide the information we have. 12 volts divided by 6 amps. That means, 12 divided by 6, that's 2 ohms. That is basically what Georg Ohm discovered. Now, using the Ohm's law circle T, we can find that missing data. Let's just assume that we don't know the electromotive force this time, but we do know the current or the intensity. Let's call that 5 amps. And we also know the resistance, let's call that 4 ohms. With these two pieces of information, we can figure out the total volts of the circuit. And that simply means we multiply those two pieces of information that we do know because they're separated by the multiplication bar, the vertical bar. And so we know that 4 times 5, that's 20. And so the electromotive pressure in this particular circuit is 20 volts. Okay, this time assume we don't know the current or the intensity. We don't know the amps, in other words. What do we know? We know the electromotive force. We're going to call that 90 volts this time. And the resistance, we're going to call that 15 ohms. So I guess what we're doing is thinking, well, 90 divided by 15, or in other words, how many 15s live inside of a 90? And if you think about it for a second, you realize that is, if we divide those, that's 6 amps. Because 2 times 15 is 30, and 3 30s is 90, so, it makes sense. Okay, so that's how we're going to use Ohm's law within a circle T. It's easier to remember math this way. Let me show you why. Here's an alternative way to memorize all of this information. First of all, volts equals amps times ohms. You would have to derive all the formulas from each other, and if you mess up, then you might get a wrong answer. Amps equals volts divided by ohms. Ohms equals volts divided by amps. I have a lot of students that have tried to just remember one of these equations and derive the other equations from the first ones and get it wrong because they got things in the wrong order. So your choice, let me go back to that one. If you look at it, which one is easier to remember? And the one on the right actually results in fewer mistakes. So we're going to use that again, Ohm's law. Ohm's law is used to analyze simple electrical circuits like this one. So if I show you this circuit and I say, well, let's say the battery is a 12-volt battery, and the lamp, let's say that is it represents 4 ohms of resistance. How many electrons are running through this thing? Or in other words, what is the intensity of the current? What are the amps? Now, that's pretty easy if you know the Ohm's law, circle T. You quickly, I didn't actually give the answer in this. I decided when I made this video just to wait for students to find the answer because it's so simple you don't even need a calculator. You take the 12 volts, you divide it by the 4 ohms, and you end up with 12 divided by 4, that current, that intensity. The amps are 3 amps. Now remember back, how many electrons is in an amp? Remember, you need to know this number. A coulomb of electrons is 6.24 times 10 to the 18th power. That is a whole lot of electrons. We got 3 of those coming through this circuit. Okay, here's another one. Give this a try. See if you can give the answer. You don't really need a calculator. These are that easy. So let's just say, oh, that cone-shaped thing, that's a heating element. I've had one of those in a fruit dryer once. But, that just heats, wires go, well, you put electrons through there to make the wires glow. That's heat. Run a fan past that, you got a heater. It's a heating element. Let's say this heating element provides 24 ohms of resistance. We don't know the voltage of the battery, but we do know that there are 5 amps running through this thing. Well, if you use Ohm's law, you can figure out what the total voltage is. Voltage is in the top, amps, ohms in the bottom, and, well, that would be 5 times 24. I kind of tend to think of these things as money. I think, well, 5 times 25, that's 5 quarters, that's 125. Now, subtract 5, and you got 120. So it's a 120-volt battery is what we're talking about here. Okay, one more. In this circuit, we have a 24-volt battery. We have 3 amps. How much resistance does this resistor provide? Now, before, when we did resistors, we used the color bands or a multimeter to figure out how much resistance, but you can also use Ohm's law to figure out the resistance of a resistor. In this case, it's pretty easy, 24 divided by 3, so you've probably already come up with the answer without even using a calculator or an abacus or whatever it is you use. The resistance is going to be 8 ohms of resistance. Okay, we're going to talk a little bit about circuit configuration. In other words, What's the difference between a series circuit and a parallel circuit? So here's an example of a series circuit. Electrons have a single pathway. They do not have any choices. They have to go through the entire circuit or none at all. Now, the perennial example of this is a string of Christmas lights where if you take one of them out or if one of them blows out, the whole string does not work. That is a series circuit. Series means things are marching in a row. Electrons are marching in a row. They are marching, they are all going one electron at a time through each one of these loads. I probably shouldn't say this, but I think of electrons as teenage boys. They love things such as, sleeping, pizza, taking naps, rock and roll music, etc. And if the electrons are like boys, it's like we kidnapped them and made them go through 3 different jobs before they could go back home. So they don't have any choice. They have to do all 3 jobs. So one of those light bulbs could be like Walmart, one could be like McDonald's, and one of them could be, a custodian somewhere. A parallel circuit, on the other hand, is more like this. Now, the reason we call this parallel is because the electrons will run in 3 branches parallel to each other. And in this case, the electrons have multiple pathways. This is like the teenage boys following the path of least resistance, getting to choose which job they get to do. And that's kind of the difference. Now, I hope you wrote this down. In a series circuit, there is only one pathway. There's only a single pathway. Parallel circuit has multiple pathways, and that's really what you need to know for now. But I probably should warn you that there is also combination series parallel, and you'll need to know how to analyze those too, but we'll deal with that later. We want to analyze this series circuit. Each lamp, we know, consumes some of the electromotive force. Let me say that the other way. Each lamp uses up some of the voltage. Voltage is pressure. Each one of these lamps consumes some of the pressure that's pushing all the electrons through these lamps. Another word for these lamps is voltage drop, which is implying how much voltage, how much pressure each one of these lamps is consuming. Sometimes the voltages can be the same, sometimes they can be different because they might be different resistances, different loads, okay? Let's assume that these lamps are, the first one is a 6-volt lamp, the next one is an 8-volt lamp, the next one is a 10-volt lamp. How much voltage is the battery providing to power each one of these lamps? This is kind of shorthand for that same question. ET means electromotive pressure total. Sometimes we just say VT for voltage total. Voltage total equals something we don't know, volts. In a series circuit, all of the pressure, that's the voltage, is consumed or used up by the resistance, in this case the lamps, in the circuit. They use up all of the voltage that the battery is willing to supply. So there's a new law. Now, I have summarized this law, so it may not be exactly the same way it's been summarized in the past that maybe you've heard of it before. But for just starting out with Kirchhoff's laws, this is going to be his first law, Kirchhoff's series law, and it has to do with voltage. I call it the KSLV law. Remember, the S stands for series, so these first 3 laws are for series only. And KSLV is, if you want to know the total voltage, add them up. So what is the total voltage? Well, to get the total voltage, we're going to add up 6 volts plus 8 volts plus 10 volts. If you're good at adding in your mind, you've probably figured out that the battery is a 24-volt battery, because you have applied Kirchhoff's series law for voltage. Okay? That's all you got to do. But there is another way to do it. If you know the battery is 24 volts, but you only know 2 of the loads, 2 of the voltages of the light bulbs, can you still figure out what the voltage is of the 3rd light bulb? Well, of course you can, because you take 24, subtract 10, that's 14, subtract 6, that leaves you with the voltage that is remaining. Same law. It's 8 volts. In case you didn't catch that, it's 8 volts. Okay. Now, we're going to analyze this series circuit a little bit different way. Each lamp also is a resistor. It resists some of the electromotive force. So this first lamp, it represents a 2 ohm source of resistance. The second one, we're going to call it a 2.67 resistor, 2.67 ohm resistor. The third one, we're going to call it a 3.33 ohm resistor. Okay? And what's the total resistance of this circuit? This is the shorthand way to ask that question. The resistance total equals something we don't know, ohms. In a series circuit, the total resistance is the sum. What does sum mean? Oh yeah, the sum means add them up. In a series circuit, the total resistance is the sum of the individual resistances. So, new law, new Kirchhoff's law. This is KSLR. KSL for resistance. You've probably already figured out that the law is KSLR is also add them up just like voltage. However, don't be confused between series laws and parallel laws. We'll talk about parallel laws in just a moment. Okay, so you got these laws. Looks like I added them up already. Hopefully you did already in your head. 3.33 ohms plus 2.67 ohms plus 2 ohms is 8 ohms. Now, a faster way to think about this sometimes is to think of these values as money. For me, it's really easy to say, well, what's $2 plus $2.67? Oh, yeah, that's $4.67. And then I add $3 more, 4, 5, 6, 7, that's $3 more. 67 cents plus 33 cents is going to round that right up to $8. So if that works better for you, that's something that works better for me. Sometimes I just convert things to money in my head and figure them out. Okay, analyze this series circuit. Using KSLV and KSLR, we have found the totals for this circuit. We know that the volts are 24 volts and the amps or the ohms are 8 ohms total because we added them both up. We know 2 out of 3 values, so we can actually figure out from this, since we know that the voltage is 24 and the resistance is 8, we can find the total amperage by using Ohm's law circle T. Ohm's law circle T, we put the 24 in, we put the 8 ohms in, and we find that the total amps at the battery, which is where the total amps are always at, is 3 amps. But let's go over to the bulbs themselves as well and check Ohm's law at each one of the loads, the bulbs. Okay, so at the left lamp we know 2 of 3 values. Voltage is 6, resistance is 2. We can use the Ohm's law to find the intensity of those amps. And so we're putting the 6 in for the volts and the 2 in for the resistance. 6 divided by 2 is 3. So it just happens to also be 3 at this lamp. Amperage turns out to be the same. Let's do this one. Might have to use your calculators for this one. I don't know if I can be trusted to do something in my head, but we know 2 of the 3 values. The voltage is 8 and the resistance is 2.67. Ohm's law, put that in there. 8 and 2.67 ohms of resistance. Tapping that onto my calculator, and I find that it is also, well, okay, if you put 2.666666, then the amps are going to be a number that need to be rounded as well, but you will also find that the number rounds very well to 3. So this one is also 3 amps. Any guesses about the last one? Amperage is the same again. Last lamp, we know 2 out of 3 values of this as well. Going to use Ohm's law to figure that out. Putting 10 volts in the top and 3.33 ohms of resistance. And 10 divided by 3.333, it's 3. Amperage is the same again. Well, the new law. Kirchhoff's series law, amps, it's the same everywhere. If you know amps in one place in a series circuit, if you know the amps in any one place, you know the amps in every place. So you can find it anywhere you want. Once you know the amps, it's flowing in one place. Then it's the same as the amps flowing in every place. If you think about that, these electrons that are flowing through here, they don't decrease in number in a series circuit. Every one of the electrons must flow through every one of the loads. They do reduce in energy, in pressure, in voltage, but they don't reduce in number. Every electron must go through all three. So that makes sense. Let's summarize the three Kirchhoff's laws. KSLV, add them up. KSLR, add them up some more. And KSLA, add them, and that's not add them up. Same everywhere. If you know one, you know them all. Did you notice these are all series laws? In a series circuit, electrons have a single pathway. These three series laws, KSLV, KSLR, and KSLA. There are also parallel laws. And these are known as, and electrons have multiple pathways here, so it won't be the same number of electrons going through each one of the loads, will it? Three parallel laws, KPL-V, KPLR, KPLA. Same group of laws. There's one for voltage, resistance, and amperage, but they're not exactly the same laws, so you can't treat series circuits mathematically the same way that you treat parallel circuits. So we're going to analyze this circuit for pressure, which means voltage. Each lamp connects directly to the battery, and so therefore each has full voltage, full pressure on each of them. So if they connect directly to the battery, and they all have 8 volts. If you know the voltage in any place, you know the voltage in every place in a pure parallel circuit. Now, that sounds the same as what we talked about before, but in series circuits, if you know something, if you know the amperage in one place, you know the amperage in every place. This time it's about voltage. If you know the voltage in any place, you know the voltage in every place. So KPL V is same everywhere. If you know the voltage in any place, you know the voltage in every place. How much voltage is the battery providing? Or in other words, ET equals something we don't know, V. Electromotive pressure, total electromotive pressure, equals something we don't know, volts. Well, it's got to be 8 volts, right? Probably knew that already. All right. Let's go for intensity, which is amps, which is current. All three words refer to the same thing. Now, electrons can choose from among the pathways on here, and each lamp uses a different intensity of electrons. So here are the electrons. They're traveling, and this first lamp, it is a 3 amp lamp. It takes 3 amps. The next lamp is a 4 amp lamp, probably different manufacturers. The next lamp is a 5 amp lamp. So to find the total intensity, well, you might think, just add them up, but that doesn't work. Add the amps at each, wait a minute, that is add them up. I was confused. Sorry about that. Parallel law, add them up. So the voltage law, the series voltage law and the series amperage law are just kind of flipped for parallel. So in this case, Kirchhoff's parallel law for amps is just add them up. So if we want to know the total amps, how much total amperage is this circuit using? What's the intensity of this parallel circuit? Well, the intensity total equals something we don't know, amps. And if you add them up, 3 plus 4 plus 5, or 7 plus 5, that's 12. 4 plus 4 plus 4 is 12. The average, it's 12 amps. Okay? So if we know that the voltage is 8 volts, and if we know the amperage is 12 amps, we can use Ohm's law at each one of these locations to figure out the piece of missing information that we don't know, namely the resistance. Let's go here. The left lamp, we know 2 out of 3 values, 8 volts, and the amps, 3 amps, right? 8 divided by 3, we remember from before, it's 2.67 ohms of resistance. That's that one. This one, 8 divided by 4, that should be pretty simple. right? 8 divided by 4, well, that's 2. This is a resistance of 2 for this lamp. Last lamp, 8 volts divided by 5. I can't do this in my head. I can't be trusted doing stuff in my head without a calculator. So, got to use my calculator. But it is a resistance of 1.6 ohms. Okay? And so let's do this. Let's do the same thing. Some people right now think, you know what? You could just add those up and you'll get the correct answer because you're adding more and more resistance. So let's do the circle T with the 8 volts and the 12 amps, see what we get. 8 volts divided by 12 amps, 0.67. 0.67 ohms is the total resistance of this circuit, which for some people is a little confusing. Wait, what? We remember in the other circuit, the more resistance you add, the more total resistance. In a parallel circuit, the more resistance you add results in less total resistance than all of the resistances combined. And for some people, that is confusing, but I'm going to explain why. How can these three resistances combine to make a smaller total resistance? If this were a series circuit, we'd just add these up, but obviously that won't work with this parallel circuit. So to understand this, I need to show you this parallel circuit. And in this parallel circuit, the electrons are going to flow beside each other in parallel, right? In this circuit, electrons will flow through a single pathway or in series. And in each circuit, we're going to put the same 3 resistors. In the parallel, we got one ohm resistor, one 2 ohm resistor, and one 3 ohm resistor. Rounded whole values to make it easy. In the series circuit, we're going to put one ohm resistor, one 2 ohm resistor, and one 3 ohm resistors. And remember, resistors slow down the flow of electrons. They reduce the pressure and they slow down the flow of electrons. That's what resistors do. The larger resistor slows the flow the most. So the 3 ohm resistor will slow the flow the most. The 1 ohm resistor will slow the flow the least. The 2 next most. The 3 ohm resistor will slow the flow the most. Well, the thing is that these resistors are in different paths on the parallel as opposed to the same path in series. So in the series circuit, the electrons are being slowed down 3 times, where the electrons can choose the path of where they want to be slowed down. So let's look at this as a race. These 2 electrons, they're going to race, right? Here's the starting line. They're going to race to the finish line. And as they race, they're going to be slowed down by resistors. So if you were a betting person, which would you bet on to get to the finish line first? Well, keep your eye on these, because here they go. They are racing towards the finish line. And as they go through, they are slowed down by each successive resistor. And as you see that they're slowed down by each successive resistor, actually I'm going to point right here. Can you see my cursor? It gets kind of small, but this is the one that we thought that was the first in. We thought it'd be the first out. But this resistor, did I call it a resistor? This electron, this coulomb of electrons, was the first one. But it was passed up by this coulomb of electrons that went through this branch. Maybe they could just be called electrons, I guess, if we want to. It's probably more accurate description. But just because one went past the finish line doesn't mean this one that we had our eye on first has gone through the finish line yet. But it did pass through the finish line before this one did, because this one was slowed down 3 times. And this one was slowed down by a 2 ohm resistor. No matter which path, it wouldn't have been slowed down as much as these I'm going to say these words wrong again. These electrons. Why did parallel win? Well, the main idea here is that more lanes allow faster travel. The proof is in Kirchhoff's laws. Over here we have the KSL resistance law, which is atom up, which means really what we have here is a single resistor of 3 plus 2 plus 1. Total resistance of this particular direction, this particular channel, this series circuit is 6 ohms. That's pretty high resistance. That slows the travel down quite a bit. Over on the parallel side, it's wonky. We'll talk about why it's wonky in a minute, but the total resistance is going to be 0.55 ohms of resistance in this scenario. Okay. Because even though we're going to be, we can actually combine these resistors into one, and if we did, the total resistance, we could replace all three of these resistors if we wanted to with a single resistor, but if we did, it would have to be a 0.55 ohm resistor. Okay. In a way, it's averaging the three speeds. That means we have lower resistance, faster travel, and so there's more lanes. And so you can see that electrons, the current of electrons, flows faster through a parallel circuit than it does through a series circuit. More lanes allow faster travel. Another way to think of that, I'm just going to line them all up this way. Alternate metaphor here. This is a dam. Okay? Reservoir. A dam. My father-in-law said, he always said, I'm not a dam fisherman. He's a stream fisherman. Anyway, getting off the subject here. This is a dam, and basically it's two dams because it's got that concrete barrier separating them back, but each of these dams is holding back a lake, and if you haven't noticed, it's a lake of strawberry Kool-Aid. Notice that more holes in the dam means more strawberry Kool-Aid gets through. More fluid gets through with more holes. I want to go back here. And so just a different metaphor to help you understand why the total resistance, every time you connect another pipe, you are adding resistance, but what you're also doing is reducing the total resistance because you're adding more holes. Okay, so looking at this now. 6.67, Jackie Chan says that's understandable. He's good with that. So how does KPL wonky work? Let's talk about that. How can these three large resistances be mathematically averaged to get the same total resistance? The real question, what's the math where you can combine these three resistances and get a smaller resistance? So here it is. KPLR, the total resistance, is equal to, write this down, these are red words, this is what we call the wonky formula. 1 divided by 1 divided by the first resistance of the first resistor, plus 1 divided by the resistance of the second resistor, and 1 divided by the resistance of the third resistor. There's 3 dots, and so forth. That just means that you keep doing this. You keep adding resistances in the denominator. If you have more loads, more lamps, more resistors. If you have fewer, then you use fewer resistances in the denominator. So let's put numbers to these. I'm going to take that 0.67 ohms, and we're going to call that the total resistance because it better equal that, because if I said it does, it better. Over here, I'm going to take the resistance of the first resistor, the resistance of the second resistor, the resistance of the third resistor. Now, you guys have calculators. You can put all this in at once. But I'm suggesting that you try it the slow way. Students that start out doing the wonky formula the slow way tend to make fewer mistakes in the answer. Try it a few times this way, then use your super atomic powered calculators, abacuses, whatever you use. But let's try it this way. 1 divided by 2.67 ohms is 0.3745 ohms. You can actually validate whether or not I'm doing this right on your calculators. 1 divided by 2 ohms happens to be half an ohm, 0.5000 ohms. 1 divided by 1.6 ohms is 0.6250. I don't know if you can hear that whistling in the background, but I'm recording, and there is a big storm going past and a lot of wind. Maybe you don't hear that. I don't know. Anyway, now we have to add up everything in the denominator. So if you add all these things up, you get this number. 1 divided by 0.4995 should be 0.67 ohms, and indeed it is. You can stop the video and try this if you haven't to see if it works. Okay, so let's summarize. Kirchhoff's series laws, Kirchhoff's parallel laws. KSL V, KSL A, KSL R, these are the series laws, VAR. KPL V, KPL A, KPL R, the total voltage, add them up. Total amperage, if you know one, you know them all. They're the same everywhere. The total resistance, add them up. KPL, the total voltage. If you know one, you know them all. They're the same everywhere. Do you see a pattern emerging here? If you see that pattern, add them up, same everywhere. Add them up, same everywhere. The next one, add them up. It really makes Kirchhoff's laws easy to memorize. As long as you remember the order is VAR, VAR, add them up, same everywhere, add them up, same everywhere, add them up, and of course, the wonky formula, because if we didn't change things up for the last one, it wouldn't confuse students, and really that's where we're in the business to confuse students, right? So the wonky formula, just restating it here, 1 divided by the first resistance of the first resistor plus 1 divided by the resistance of the second resistor, and 1 divided by the resistance of the third resistor, and so forth. Okay, so also, while we're at it, we're going to be using Ohm's law as well as the 6 Kirchhoff's laws. Of course, you remember Ohm's law. It's VAR as well. And if there's 2 that you know, but 1 you don't know, then you can find the one you don't know by using Ohm's law. All right. So I just want to point out that sometimes we don't use V because we're trying to confuse students. Sometimes we'll use electromotive pressure, or E, instead of V. Well, that's electromotive pressure. That's V. Same thing. A, sometimes we will swap that out for the intensity, right? The intensity or current or amps, okay? R, sometimes we'll swap that out just to confuse people with the little horseshoe, the omega, the Greek letter omega, which reminds us that it was Georg Ohm, whose last name was Ohm, joined the resistance, all that stuff. Ohms of resistance, okay? So far, we've been discussing what is a basic circuit. Simplified Ohm's law math, resistance to flow of electricity, introduction to circuits, simple circuit analysis using Ohm's law, circuit analysis using Kirchhoff's series law, series versus parallel circuits, circuit analysis using Kirchhoff's parallel laws, and next time in part 4, we're going to talk about what kind of a name is Kirchhoff anyway. Practice series circuit analysis. Going to do some practice. We're going to talk about what is power. We're going to talk about some practice final exam style series circuits and some practice final exam style parallel circuits, and simple circuit analysis using Ohm's law, and circuit analysis using Kirchhoff's series laws, series versus parallel circuits. This is pretty much, all those last 5 bullets are a lot of the same thing, just different perspectives. So anyway, that's what we'll work on next time in presentation number 4. Thank you for watching.